Welcome to this comprehensive tutorial on LeetCode problem number 53, maximum subarray. In this session, we will break down every aspect of this fundamental problem, one which is not only popular in coding interviews but also offers valuable dynamic programming concepts. We will look at the problem statement, review the various examples and edge cases, and dig deep into multiple solution strategies, including brute force approaches and the classic optimal dynamic programming method. Once the approach is clear, we will provide detailed step-by-step algorithm explanations, walk through full Python and Java implementations, and demonstrate exactly how the solution arrives at the answer with concrete examples. Finally, you will understand the trade-offs in time and space complexity, recognize common pitfalls, and be ready to ace this problem in any interview. By the end, you'll be comfortable implementing the maximum subarray solution in both Python and Java, handling all constraints and edge cases with confidence. Let's start by reading the problem statement for LeetCode problem number 53, maximum subarray. You are given an integer array nums. Your task is to find the contiguous subarray within nums that has the largest possible sum and return what that sum is. The subarray must be contiguous, and it needs to contain at least one element. Now let's look at the examples provided. In example 1, you have the array -2, 1, -3, 4, -1, 2, 1, -5, 4. The largest contiguous subarray sum is from the subarray 4, -1, 2, 1, which adds up to a sum of 6. This means the function should return 6 for this input. In example 2, the array is just 1. Here, the only contiguous subarray possible is the entire array itself, so the output is 1. In example 3, the array is 5, 4, -1, 7, 8. Although there is a negative number in there, the sum is maximized by taking the whole array as the subarray, yielding the output 23. Let's highlight some constraints and edge cases. The length of the array nums is between 1 and 100,000, making brute force approaches potentially inefficient. Each number in the array can be as small as -10,000 or as large as 10,000. It is also important to consider edge cases. When the array has only one number, the answer is just that number, whether positive or negative. If all numbers are negative, the answer is the single least negative number. And if all numbers are positive, the answer is the sum of the entire array. Make sure to handle these edge conditions in any implementation. Now, let's analyze the main approaches for LeetCode problem number 53. The brute force solution tries every possible subarray, computes their sums, and tracks the maximum. However, this takes quadratic time and isn't feasible for large input sizes. A second approach uses prefix sums. Although prefix sums can speed up subarray sum computation, checking all pairs of start and end indices is still O(n) squared overall. The best approach here is dynamic programming, specifically Cadon's algorithm. It only needs one pass through the array, making it truly optimal, and automatically adapts to all the edge cases that the constraints require. That's why practically every interviewer expects this solution. Alternative, more advanced strategies like divide and conquer can bring the runtime down to O(n) log n, which is still worse than Cadon's, but it's good to know for variation and discussion. Segment trees would only be necessary if you had to support many subarray sum queries, which isn't the case here. Let's proceed by exploring how Cadon's algorithm solves this problem efficiently. Let's break down Cadon's algorithm, which is the optimal dynamic programming solution for LeetCode problem number 53. The algorithm maintains two important variables as it traverses the array, a current_sum, representing the maximum sum ending at the current index, and a max_sum, tracking the overall best sum found so far. Both start at the first element. Then, for every index after the first, you have a simple decision: is it better to extend the previous subarray by adding the current number, or start a new subarray at this element? You pick whichever is larger, assigning that to current_sum, and always update max_sum if you find a new maximum. This logic has a powerful effect. If a negative subarray or valley is encountered, the algorithm resets at the next positive number, ensuring the sum is always the largest possible. No explicit handling of edge cases is required, since Kadon's algorithm naturally covers arrays with all negative, all positive, or mixed values. Moving deeper into the implementation details, you always initialize current_sum and max_sum with the first element of the array. This is essential because if the array is all negative, you want to guarantee that the result is not mistakenly set to 0 or a positive number not present in the input. As you iterate, you use the max function to decide whether to start a new subarray or continue the existing one. The algorithm maintains O(n) runtime because you only ever go through the array once, with no nested loops. Let's consider part of our earlier example, -2, 1, -3, 4, -1, 2, 1, -5, 4. After the first element, current_sum and max_sum start as -2. At index 1, you compare 1 and -2 plus 1. It's better to start anew at 1. As you continue through the array, the logic automatically adapts, and in the end, max_sum lands at 6, which is the correct answer. No special handling for all negative or all positive cases is required. Here's the complete Python implementation for LeetCode problem number 53, maximum subarray. Let's step through it line by line. We define a solution class with a single function, max_subarray, which takes in the list nums. We initialize both current_sum and max_sum as the first element. This correctly handles arrays with negative numbers. Then, we iterate through each number in num starting from the second one. For each number, we decide if it's better to start a new subarray at this point, or to include the number in the current sum. Next, we check if the current_sum beats max_sum so far and update it if necessary. In the end, the function returns the max_sum, which holds the largest sum for any contiguous subarray. Now let's review the equivalent Java implementation for LeetCode problem number 53. The logic is the same as our Python solution. We define a solution class with a public max_subarray method. CurrentSum and maxSum are both initialized to the first element of the input array. We use a for loop to iterate from the second element to the end, updating CurrentSum as the maximum of either starting anew at nums, I, or adding nums, I, to the current sum. MaxSum is updated accordingly if a new maximum is found. Key differences from Python include static typing, explicit array indexing, and use of math.max for comparisons. Finally, we return maxSum as the answer. Let's follow the calculation for example 1 from start to finish. The input is -2, 1, -3, 4, -1, 2, 1, -5, 4. Initially, both CurrentSum and maxSum are -2. When we read in 1, CurrentSum becomes 1 and maxSum updates to 1 as well. At -3, CurrentSum drops to -2, but maxSum holds at 1. When we reach 4, it's better to start a new subarray, so CurrentSum is set to 4 and maxSum now becomes 4. As we proceed, each step either adds to CurrentSum or resets it, updating maxSum whenever a larger value is found. The largest sum reached is 6, which occurs after processing the subarray, 4-1, 2, 1. This matches the correct output. Now, let's examine an all-negative input, such as -3, -2, -1, -4. CurrentSum is always reset since adding further negatives never helps. So, the algorithm keeps updating maxSum with higher single negative numbers, and the answer is -1 from subarray, -1. With all positive numbers, for instance, 2, 4, 6, 1, CurrentSum and maxSum both accumulate as we progress. The answer is the total sum, which is 13. These cases show how Kadon's algorithm automatically adapts to different types of input arrays. Let's analyze the time and space requirements for each method. Brute force and prefix sum methods run in quadratic time and quickly become impractical as the array size increases. Kadon's algorithm, on the other hand, is linear in time because it only scans the array once. It is also optimal in space, requiring only a few variables regardless of input size, so it is constant extra space. In context, Kadon's is the best choice for a single maximum subarray query. Divide and conquer methods are slower and rarely needed. In summary, for LeetCode problem number 53, use Cadon's algorithm, O, N, time and O, 1, space. LeetCode problem number 53 serves as the basis for many related questions. For example, LeetCode 918 asks about the maximum subarray sum in a circular array, where wrapping is allowed, and LeetCode 152 involves products instead of sums. In practice, one common bug is initializing the algorithm with 0 instead of the first element, leading to incorrect answers with all negative input arrays. Interviewers are often looking for a clean, efficient solution, so avoid over-engineering with unnecessary data structures or extra memory. It's a great idea to manually work through a few cases to get comfortable. Knowing when to use which approach, and clearly justifying it in interviews, will set your answer apart. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!